Hello, and welcome to General Chemistry 2. My name is Daniel, and in this video we're going to be looking at chemical kinetics. Now, kinetics is just a study of the speed of chemical reactions. The reaction rate is just how quickly reactants are going to be converted into products. And there's multiple different ways that we can look at reaction rate. We can look at it in terms of straight reaction rate. We can look at it through these things called rate laws, differential and integrated rate laws, as well as half-lives. So let's just start out by talking about what exactly we mean when we're talking about the reaction rate, the speed at which a reaction occurs. So let's say we have 2 points. We have concentration A1 at time 1, and then concentration 2 at time 2. As a reaction progresses forward, reactants are converted to products. So as we go on, the concentration of the reactants will be decreasing as time progresses because it'll be being converted into products. So if we wanted to do a basic definition of rate, we would take the concentration at time 2 minus the concentration at time 1 over the change in time in that period, and that would give us an average rate for our reaction, assuming that it stays constant. We can write that as we do here on the bottom, just with these delta concentration over delta T, where delta just means a change in anything. So that would be A2 minus A1 on top, over T2 minus T1 on the bottom, just like that. So that's our most basic definition for a reaction rate. Let's look at a graphical representation of a reaction in progress. So let's say we have the decomposition of NO2. It forms 2NO and O2. So we can clearly see here that this line going down must be the NO2 because it's a reactant, so that means it's going decreasing its concentration. And then the green line is NO, and the purple line is O2. So this is just a graph of concentration over time. And there's two main important points that we can see here. The first one is that in this reaction, the reaction rate is changing as time goes on. We see that because if we take the slope of the line at any of these points, that's our reaction rate. So what we see then is that the reaction rate's greatest in the beginning and then slowly tapers off as we get closer and closer to a kind of equilibrium between the two species. So what that means then is that we can take two different kinds of rates. The first one we could take is known as an instantaneous rate. An instantaneous rate is just the rate at a certain time in the reaction. So all we would do there, if we wanted to find the instantaneous rate, is we just take a point like this one over here, draw the tangent line to that point, and the slope of that tangent line is our rate. If we wanted to take the average rate is just the average of instantaneous rates throughout a period in a reaction. So if we wanted to find an average rate, we could take, say, a point here and a point here. They have their respective instantaneous rates. And then we would just take the difference between them over the time difference in between those two rates occurring. Okay, so instantaneous rate is at one point, average rate is at a series of points. The other takeaway we can see here is that the reaction rates for all of these species aren't equal. We can see especially that occurring in between O2 and NO. So if we look here, for example, let's take this point. I'll do this in red actually. We see that the slope for the NO is greater than the slope for the O2, which means that NO is being produced more quickly than O2. And that makes sense because if we look at the stoichiometry here, we see that, let's say we have 2 molecules of NO2 dissociate. We get 2 moles of NO and then only 1 mole of O2. So it makes sense to say that O2 is going to be formed more slowly than NO. And that's the reason for the discrepancy in the reaction rates here. Now, when we have a system like this, we can quantify the reaction rates based on the disappearance of a reactant or the formation of a product. So let's say we have some instantaneous rates. At 250 seconds, we have the following. the rate of O2 production is at 4.3 times 10 to the negative 6. And then the rates of NO production and NO2 consumption are both 8.6 times 10 to the negative 6. It's just important to remember that the products are increasing their concentration. The reactant is decreasing its concentration. Okay, so let's define the rate in terms of the change in concentration of these species. So let's say we define the rate as follows. Let's say rate is equal to the change in NO2 over the change in time. What we can also say is that number is going to be equivalent to the positive of the change in NO over time. We have this negative sign here for NO2 because it's decreasing. And then finally, if we wanted to do this quantitatively, we see that 2 times the reaction rate of O2 is equal to the same thing. It's mathematically equivalent. What that means, though, is that delta O2 over time is just equal to 1/2 that of NO2. And that makes sense both from our graph and from our stoichiometry that we saw in the reaction. So one of the important things we'll have to be able to do is we'll have to be able to interconvert between rates. We'll have to say, take the rate at which a reactant is disappearing and convert it into a rate at which some kind of product is appearing. So take a minute and pause the video and see if you can figure this out. Here we have this reaction. pH3 is being consumed at a rate of 0.0048 moles per second. Based on the stoichiometry we see in this reaction, see if you can figure out what the rate of production for H2 would be. Okay, I'll just give you a second to pause the video and try that out. Okay, so we know that the rate of consumption of pH3 is 0.0048, and that's in just moles per second. So what we have to do is we have to convert this rate. We can write it like this. And we have to somehow convert it to the same expression, except now for H2. So what we could see here is that the rate of pH3 being consumed is 2/3 that of H2. What that means then is we can write the following expression and they would be equivalent to one another. So if we say that the change in concentration of pH3 over time is going to be mathematically equal to 2/3 the rate of production of H2. That 2/3 just reduced from, 4/6. Okay, so based on the stoichiometry of the reaction, we see that these two expressions are mathematically equivalent to one another. So what we can do now is simply plug in our rate for pH3, and then we can solve for our rate for H2. So that's going to look like this. We have 0.0048 moles per second equals 2/3 delta H2 over delta T. And so what we'll find then is that our rate of appearance for H2 is simply going to equal 0.0072 moles per second. And it makes sense that that is higher than the rate of consumption of pH3 because of the stoichiometry we see in this reaction. So for every 4 moles of pH3 consumed, we're getting 6 moles of H2. Okay, so the most important thing to do with these is set up this initial equation, this having everything mathematically equivalent on both sides. Here we said that the rate of use of pH3 is equal to 2/3 the rate of appearance of H2 from a purely numerical standpoint. And then we just use that to simply, solve for that rate of appearance. You'll see a lot more of these in the workshop. It's very important that you're able to do this. For now, though, we're going to get into what's known as rate laws. So we've only been talking about rate in terms of just reactant concentrations. What we can do is we can express the rate